Okay, chemistry scholars, it's time for a little tutorial on metal reduction. Metal reduction. Okay, so right here we've got copper mineral here, copper containing mineral. Remember, a mineral is something that we pull out of the ground that contains metal ions. And this right here, this mineral that we have right here, is a mineral that contains Cu2 plus ions. Okay, that's good. We've got copper in this mineral, but it's Cu2 plus, and we are unable to use ions to build things like structures, to make things like jewelry, to make wiring, other electronic devices, even things like pots and pans. Ions simply don't stick together. So what we need to do is, let me get rid of my arrow there for a second. What we need to do is convert the ions in a chemical process, some kind of metallurgy process, to solid copper. Of course, this process is called a reduction process. So let's take a look at a big picture situation here. We have our copper mineral, which we've mined. We've pulled it out of the ground. The copper, when we pull it out of the ground, is in the form of ions. Not good. Okay, not good. We can't use that. But what we need to do is specifically reduce the copper, and that's when we get our copper metal. And that's a good thing, because that's what we can use. This reduction process right here, this reduction process, as we've learned, involves electrons. Specifically, the copper, each copper ion that we start out with right here, gains 2 electrons to become our stable copper atom. Okay, to take this idea of reduction one step further, reduction, as we stated earlier, is a process that involves adding electrons to an ion to get the metal, the neutral atom, in this case, neutral copper. So we're starting out with Cu2 plus, we're adding 2 electrons to get copper. In this case, our ion has been reduced, the charge has been reduced because we've added 2 electrons to Cu2 plus, and the result is a neutral atom. Well, as we know in science, we can't get something for nothing. And I'll change up my color here. This is really important right here. These 2 electrons, we can't just pull them out of anywhere. They just don't show up when we want them to. So that's where the oxidation comes from. That's where the oxidation comes from. Oxidation is a process that is the opposite of reduction. For example, if I have something like something that likes to give away its electrons, for example, something like magnesium. Magnesium likes to give away its electrons, and in doing so becomes positive. So here I've got a metal, a substance that's pretty high on the activity series, likes to give away its electrons, specifically these 2 electrons, and as a result, in the end, what we have is the magnesium ion. Actually, my charge is not correct there. You might have noticed that. Just get my pen back. I need a 2 plus up there. So, the red process right here, this red process right here, indicates reduction because I'm adding 2 electrons to my copper ions to get copper. This blue process right here is oxidation, meaning my magnesium is given up 2 electrons and my result is a magnesium ion. Now, you might be noticing that these electrons right here are up to something, specifically the electrons that are given up by magnesium here. If I play my cards right, those electrons, or these electrons right here, can be the electrons that copper picks up to become solid copper. So if I play my cards right and I run my reaction properly, I can reduce copper with 2 electrons from magnesium. Okay, this magnesium lost these electrons to produce what I want, which is copper. Okay, let's take another close look, or a closer look at what's going on here. In the previous slide, what we saw was our copper being reduced, or copper ion being reduced to form plain old copper. Then we showed that magnesium is oxidized to produce the magnesium ion. Specifically, it was the magnesium that gave up 2 electrons that found a new home in our copper ion and turned our copper ion into copper. So if we get our pen back here, we can show that. Specifically, magnesium loses 2 electrons, gives them to copper. On the other side of the arrow, we see what magnesium has become, and that's an ion. And look at our copper now. The charge has been reduced from +2 to nothing, or 0, and that's what we want. So in this case, what we say is magnesium has lost electrons and been oxidized, which happens just before the Cu 2+ is reduced. Okay, so in total, this is what we call a redox. And here's an abbreviation for a reaction. A redox reaction, where reduction and oxidation have taken place in tandem. Electrons have been transferred from whatever's oxidized to whatever's reduced, and in the end we get what we're looking for. So if you remember that copper mineral that we saw, that copper mineral had all this stuff, copper 2+, where the mineral is made up of these ions. What we need to do is treat that mineral with something that's willing to give up electrons. In this case, it was magnesium. And then we have the end result here, which is copper. Remember, the process is a redox process, but more specifically, we call it a metallurgy process. That's a word we've talked about in class, a metallurgy process. And that's a process that gives us the metal that we're looking for. Okay, let's take another look at a reduction-oxidation reaction in order to produce a metal. And we're going to use the help of a picture here. This is a before and after picture. It's very similar to what we did in lab. Here's the before, here's the after. Looking closely at what's going on inside this chamber here, which is just like one of the well plates that we used in our lab. We see copper right here, solid copper atoms, all bunched together. Okay, these are neutral atoms making up copper metal. We see the wire right here. Well, these guys out here, no surprise, these are ions dissolved in water. Okay, and specifically, these are, make sure my pen's the right size here. Okay, these are silver atoms. Excuse me, silver ions. Okay. So these guys right here are silver ions. They're dissolved in the water out here. They're dissolved in the water. Yeah, there's nitrate up in here, but remember, the silver is separate from the nitrate. The silver is separate from the nitrate. It's been separated, it's dissolved. We're only concerned about the silvers here. Now what we're going to do is react that silver with the copper. That's solid copper, it's unionized. Alright, and as time goes by, we go over to the right hand side and we can see that something's happened in here. And specifically, we see a little switcheroo. That is to say, these silvers, which were over here, in an ionized form, are now solid metal. So that means no longer is the silver ionized. No longer is the silver ionized. What has happened is that copper has left the wire and is now dissolved out in the solution. And that's why we see these guys up here. Okay, the copper atoms jumped out and are now dissolved out in here. That's why we see that bluish color. I'll explain a little bit more of that in class. But copper turns water, copper ions turns water blue like that. It's pretty. Now, we have to look closely at what's going on here. Our matter is balanced. Okay, we have a silver there and a silver here and a copper here and a copper here. But charges are not balanced, so we need to take care of that. Remember, we can add coefficients. What we need to do here is first balance the charges. I've got a 2+ charge on this side. I've got a 1+ charge on this side. The only way I can balance these charges is by putting a 2 right here in front of the silver. Okay, but now unfortunately my silvers are unbalanced, so I can come over here and put a 2 there. So now I have 2 silvers on each side. I've got 1 copper on each side. The matter's balanced. The charges are balanced. And just to make a point over here, if you notice, these are 2+ ions. Okay, when copper jumps out, 2 electrons are given up by copper. 2 electrons are given up by copper. That means 1 copper over here can reduce 2 silvers, because each silver only has a +1 charge, and so each silver only needs 1 electron. So a copper gives away 2 electrons, 1 electron to each silver. Then I produce 2 silver atoms, and there we go. There's the pretty silver metal that's literally growing on top of the copper wire below. And that's how we make solid silver.